I am extremely honored to be, to receiving this award, and I'm extremely thankful to the university and to David and to your distinguished dean to supporting this award, because I can tell you from a woman who in the field that really has always been feeling very strongly about the importance of career advancement of women in science. I've been watching this award for a very long time. I've been watching who was the winners, and the 15 women, 14 women, I guess, I'm the number 15, right? I'm extremely flattered to be part of that. Of that group. So I'm going to start with my lecture, but I also would like to make sure that we're going to have time at the end to take questions about whatever, gender representation, inclusiveness, women in science, and this my specific topic on public health and health effects of air pollution. So what I'm going to talk to you about is one of my research topic has been really to understand the health effects of air pollution. So everything started one of the most, I would say, very telling episode, which really brought tremendous amount of attention about health effects of air pollution was, they call it the famous London fog, 1952. And so that picture was made at 10 in the morning, and the visibility was so poor because of amount of pollution. And what this graph shows is basically during this week in December, you see that the level of smoke and sulfur dioxide increase, and that will be how the number of deaths increase. And clearly, you don't need fancy statistical models or being a data scientist to see what was happening. So that's really started, this movement over the years, and which was also prominent in the United States, but really to really watch very carefully health effects of air pollution, of course, not only in the US, but most importantly, and also in other countries. And I think now both China and India are the ones that have an enormous higher level of air pollution. And so, in China, it's becoming actually almost a fashion statement. And, to just also give you a sense, like, people running a marathon with gas masks. In the United States, we have been making an enormous amount of progress. There was the Clean Air Act that passed in the 1970s, where I'm going to speak about it a little in a second, where really we have the Supreme Court passed the law that every year there will be, every few years, the Environmental Protection Agency will review all of the amount of evidence of the health effects of air pollution. And if there was a lot of evidence about health, the harmful effect of air pollution, people and the different states and the county, we need to put action in places to reduce the level. Now, lately, with our new EPA administrator, Gina McCarthy, she has been telling scientists that it's not enough anymore to simply say, once again, health effects, the level of pollution in the air are harmful to you. What she really wanted to know is what can we do about it, which gets to the point to which I'm going to speak for in a moment of causal inference. So the EPA administrator is calling for sound scientific evidence to systematically evaluate the effectiveness of control strategy. So there are many, many different ways we can do to reduce the level of pollution in the air, but what is the most cost effective? And above and beyond the cost, what is the most effective to public health? So to give you a little bit of more context, as I was mentioning, the Clean Air Act is one of the most important laws for protecting public health and the environment in the United States. So as I was mentioning, the Clean Air Act requires the EPA administrator to set national ambient air quality standard for pollutants for which air quality criteria are listed. By intent, the NAAQS must protect susceptible groups within the US population with an adequate margin of safety. And so in terms of the benefit and cost of the Clean Air Act, you can see that it's been quantified that clearly the benefit by far outweigh the cost. Now, in the research, there have been now two questions. And one thing that the research has been challenged lately by interest parties is whether there is really, you can estimate and find a causal link between exposure to air pollution and health versus just an association. So I don't know how many of you are familiar, but in statistics, in addition of all of the wealth of regression model where you estimate an association between X and Y, controlling for other covariates, there is also another field which is becoming now very prominent, which is called causal inference methodology. And the interested party, I mean mostly industry, has been challenging a lot of the evidence of air pollution research, saying, well, if you cannot show that there is a causal effect, that air pollution kills people, then we don't have enough rigorous evidence to justify regulation. And so basically, they have been challenging me and many of the colleagues, and really the statistical community and the public health community, and say, everything you've done so far, that you're estimating association using regression model, we don't believe it anymore. You need to show me causality. So the evidence about health effects of air pollution is actually pretty strong and pretty consistent. So these are just a slide that shows all of the different, well, a subset, actually, of all the different cohort studies. They have shown association between exposure to fine particulate matter and increased risk of cardiovascular death. And so these are all listed by the different authors and so on. And so clearly, these are studies on different population, a different time frame, different measures. But bottom line is that you can see that the evidence is there. So as I said, the criticism now, and historically, interested party wanted to challenge the epidemiological evidence to stop regulation. And so now it's interesting that the type of challenge they are really raising is, well, all of this evidence, all of these studies only show association. Because these are results of regression model. These are results of a Cox proportional hazard model, a Poisson regression model, logistic regression. So all of the stuff that you study regularly. And so we can trust this. We want to, unless you show causality, or they said, well, now there is all of this new theory and all of this new methodology that estimate causal effect. And I don't know how many of you are familiar, I'm just giving you name, propensity score, marginal structure model, all of the literature by Don Rubin, Jamie Robbins, which by the way are colleagues of mine, phenomenal literature. But they're saying unless you use this sophisticated method and you prove causality, we're not going to trust all of this. And so my goal is actually, in my next 15, 20 minutes, is actually to tell you that there is really not, that this distinction really does not exist. It's not really a question of which methodology or which statistical approach you use. It's just a question of thinking about basic principle of how you do an estimation. And so I'm going to show you a little bit of the basic principle that I think you all consider anytime you analyze a data set, which is not really this dichotomy, causality versus not causality. So mythbusters, right? So I wanted to dispel the myths, such as the following. Analysis methods are either causal, you either do causal inference, and so what you do is like trustworthy, or you just fit a regression model, it's a second level. I wanted to dispel that myth. Studies that use causal analysis are always more trustworthy. Causal inference methods are fancy statistical methods that nobody can understand. So what causal inference is not, and many people claim that, is not magic. It's not a silver bullet that, because I use a causal inference fancy method, now I found out the truth. A specific method, a type of modeling techniques, and way to automatically generate scientific truth. Bottom line is, it's never, easy. It's never like, okay, because I'm using this method, I can give you the truth. There is always more that is behind, right? So what causal inference is, I think that is considered in the right way, is actually, I would say, a more rigorous way of analyzing data and thinking about the assumptions. So it's a general analytic perspective to frame scientific questions to be answered with observed data. So if I reduce the level of pollution from this level to this level, what will be the consequence in public, in health outcome? And how do I make sure that when I estimate the causal effect of, for example, a regulatory action? So let's say that we are shutting down all coal power plants. Well, what will be the causal effect by going from a situation where we have an X% of our power plants in the United States fueled by coal versus not, right? So it's framing the scientific question, clarifying common threats to the validity, okay? So what are the threats? And I'm going to tell you one of the main threats. And then increasing the transparencies of the assumption that we make. So now, PRELUDE, there is a situation where you can address causality. And, it's a randomized trial. And you toss a coin. You have every person is randomized to the treatment or the control. And that is wonderful. Why? Because the value of the randomization is that people that get the treatment and people that don't get the treatment, on average, will be similar to each other. So in that case, I can estimate the causal effect because I can always assume that my potential outcome, what would have happened to me if I did not take the drug, can be fair from the population that did not take the drug. Because the population that didn't take the drug, it's not systematically different from the population that take the drug. So that's the beauty of the randomization. The problem is in public health, in most of the problem in public health, you can randomize. We can, I'm going to toss the coin and then we send David to breathe pollution and you not to breathe pollution, right? We can do that, right? I mean, we do it with mice. We can do it with control study. But even in that situation, it never mimics the real life, especially in the context of air pollution, the context of smoking, in context of water pollution. I mean, you name it. In most of the public health problem, we cannot randomize. So if you're a student of public health, and unless you're working in basic science, most of the time you will be analyzing observational data. And so you want to extract causal inference from analysis of observational data, but you don't have the power of the randomization. And so there is really a continuous, goes from correlation study. I mean, I'm sure you all know the myth. Clearly, if you take one variable, another variable correlate, that doesn't mean that one causes the other, right? So there is a classical multiple example, I'm sure, that you see. There was this famous, I think, you always see, if you Google correlation is not causation, the first plot that shows is a number of deaths in the swimming pool perfectly correlated with number of movies of Nicolas Cage or something like that. I mean, there are all of that stuff, right? We all know that. Then there are observational study, and depends on how you analyze them, you can get closer and closer to randomization. And the goal is to analyze an observational study so then you can mimic and get closer as possible to a situation of a randomized study. Yeah, so that's the role of randomization, and causation is easier, but we can randomize, in the context of health effects of air pollution. And so what I wanted to say is that judging a study potential for estimating a causal effect should pertain primarily to the design of the study. And so I'm going to give you a specific example. And how well you have designed a study so then you can approximate a randomized study. And so question like, and this is very, I would say, instrumental and basic, but so important. How many times, I'm asking you a question, how many times you start analyzing a data set without spending enough time thinking, what is the question? What I'm asking, okay? So first is, what are the treatment groups that are being compared? I am asking, even in the context of air pollution, I'm asking what's the causal effect of reducing level of pollution from this level to this level, or I'm asking the causal effect of reducing traffic, who then will reduce pollution. I'm asking, what's the control group? I'm asking in terms of time, I'm thinking in terms of space. So what is the question, right? And so then, when you identify how is a control group constructed? So again, in randomization, the control group is automatic. You know, you have people assigned to the treatment, not treatment, high pollution or low pollution. Automatically, they are the same. So one is the control group from the other. In observational study, people that will, by living in areas that breed high pollution, might not be the same of people that live in an area that breed low pollution. So if you take Albuquerque, New Mexico, and if you take New York City, people in Albuquerque, New Mexico might breathe a lower level of particulate matter than people in New York. Can you assume that people in New York can be an adequate control group for health experience of people in Albuquerque? Oh, no, they are very different. So if we need to find a control group for people that live in Albuquerque, how do we do that? Do we take a near county that has the same education, socioeconomic status, health behavior than Albuquerque, but breathe high pollution? So these are the questions that we all, as a public health quantitative expert, we need to ask ourselves before thinking, I'm going to use this fancy method on this other fancy method. So one of the huge issues about analysis of observational study is confounding. And so I was hinting into that. And many of you might be very familiar. And that's what I was going to say, is that every time you don't have a randomization, and you want to estimate, for example, what's the causal effect of breathing high pollution level versus low pollution level on health, you need to think about all of the other things that are different between people that breathe high pollution level versus low pollution level, and they can confound, right? So if people that breathe high pollution level also are in low socioeconomic status, they might experience a more health outcome, but not because of the pollution, because of the socioeconomic status. So there are two key things. One is, what are the confounders that make the groups that I'm trying to compare not representative of each other? And then how I'm adjusting for the confounders. And so let me tell you a trick. All of these causal inference methods that you read out there in the literature, basically what they do is try to find a better way of adjusting for the confounders. But they're not going to give you a free lunch in figuring out who is the control group and which confounders you need to adjust for. So they're only solving, like really at the end of the empirical investigation, but there is so much behind that we all have to think. So I think I just want to leave you a little bit with a checklist and thinking when you are analyzing an observational study, and then I'm going to give you an example in the context of air pollution and health. I think these are the things you really wanted to think about. Above and beyond of whatever fancy statistical method or non-fancy statistical method you're going to use. So in public health, you're going to deal with an observational study. You want to look at the effect of an HIV treatment on health, effect of air pollution on health, effect of passive smoking, effect of a micronutrient supplementation in developing country. These are type of questions, right, that we analyze all the time. And so you want to think about what type of design. Is an observational study? Is it cohort studies? What is the randomized? Okay, that's a critical question. What is the randomized experiment that you wish you have had? Okay, and that is always a good question to ask. What is the action of exposure level being compared? What is the causal effect of interest? What are the potential outcomes being compared? So this concept of potential outcome is actually very helpful. And the potential outcome, it's one of the basic concepts of causal inference, is about thinking, so if I have a treatment you are going to observe the response from, from my treatment. And the potential outcome for me will be what would have been my response if instead of giving the treatment, you would have given me the placebo. And the goal is to construct an adequate control group so that I can estimate my potential outcome from the control group, okay? So I can give you the example here in this room, right? So I am getting an anti-anxiety drug to, make myself calmer. So you're going to measure my blood pressure 10 minutes after I get my anti-anxiety drug, right? So you can measure my blood pressure. Now, you would like to know what my blood pressure would have been absent the fact I'm taking the anti-anxiety drug. And so I'm just going to look in this room, and I'm going to think about, a woman that has similar anxiety symptoms that are pretty much my same weight, pretty much my same age, and same craziness. And then you will be my control group. Then I'm going to take all of the average of the blood pressure of the women in this room that are similar as possible to me who did not take the drug. And that's a way to get closer of what my response would have been absent taking the drug. Okay? So I think that's what's called matching. Okay? And when you feed a regression model and you include covariate into the model, you're just doing a parametric version of matching. And so it's a different estimation, but the concept is what really counts. So I want to give you an example and just walk you through a specific example in the context of one of the most influential studies. I would say this was the most influential study in air pollution and health. And really, it's called the landmark study. This is called, it's called the 6 city studies. It was really a paper published in New England Journal of Medicine in 1993, which showed, in very strong evidence of a relationship between exposure to pollution and mortality. This was an observational study. There is no causal inference whatsoever. And has been heavily criticized because it doesn't do causal inference, okay? And I just want to walk you through of how you analyze this study thinking about causal inference perspective. So the study is pretty simple, actually. Let me just show you just some data. So they have 6 cities. They're shown like there. And it's a prospective cohort studies. They have a cohort of approximately 8,000 people. They live in these 6 cities. And they follow these people over time. And they see as whether people that live in cities that have a higher pollution level have higher mortality. So these are the pollution level measured in the 6 cities. So Steubenville, Ohio was the highest polluted city. You see they have the higher level of pollution throughout the year. Then you have Erie, St. Louis, Watertown, Topeka, and Portage. Okay? For simplicity, I'm just going to say for a moment that I'm thinking about comparing the survival experience for people that live in a very low polluted area versus a very high polluted area. What they really did is, so first of all, what is the causal effect of interest? The causal effect of interest is if you transition from a situation where you breathe very low pollution level to high pollution level, what's going to be your increase in mortality? What will be the idea of randomization? Well, the idea of randomized side that you take 8,000 people and you randomize them, and you say, okay, now you're gonna live in Portage for 15 years, you're gonna live in Steubenville another 15 years. We couldn't do that. But if we could have done that, okay, so let's take this room. And I'm just going to say, okay, 1, 2, 3, 4 randomly. You go here, you go here, you go here, you go here. Well, then it would have been a perfect randomized study. I would have followed you for 15 years. And on average, people that will live here, here, here will be all similar to each other. But that's not what happened in the study. That's not what's happened with an observational study. We follow people that live in Portage, Topeka, and they're different, right? So the ideal randomized study would be that assuming that people that live in these different cities will be similar to each other, but clearly they're not. And also, they could have potentially do 15 different analyses, so like comparing each pairwise comparison. What they did instead, they fit a regression model. When you fit a regression model and you put your exposure to this level, it's basically making a parametric assumption about what the relationship between pollution and health. So what type of design is an observational study? What is the randomized experiment we wish we could have done? Well, we wish we would have done an experiment with 6 treatment groups where people with certain characteristics are randomized to one of the 6 pollution levels. Again, we can do that, but that's what we wish we could have done, right? What is the action of exposure being compared? Well, action A, living in a high pollutant city, action B, living in a low pollutant cities, or any different comparison, right? And for simplicity, because it's nothing really more intuitive, let's say that really we want to focus on estimating the causal effect of living in A versus B, okay? So this is what is the idea about potential outcome, okay? So how do I estimate the causal effect of being exposed to air pollution if I go from Steubenville, Ohio, to Portage, okay? And that's where it comes to this concept of potential outcome. So what's the concept of potential? So let's say, and by the way, I hope this is not anyone's family relative. I just dragged this from the web. I don't know what this person is. So, Jane looked to me, someone who can live in Steubenville, Ohio, and all her life. And what do we know about? So I want to estimate the causal effect of breathing pollution at high level as a Steubenville, Ohio, versus breathing low pollution level in Portage, okay? So I take Jane, and so we know Jane is a member of my cohort, and I know that she lives in Steubenville, Ohio. She's 55 years old. She's an elementary school teacher. She doesn't smoke. She has an average BMI of 50. She's married. She drinks wine, and she dies at 78 years old. Okay, so I know all of these things from my cohort study, right? Now I need to figure out the potential to estimate the causal effect of exposure to high pollution versus exposure to low pollution in the population. For every person, I need to calculate the potential outcome. So how long more Jane would have lived if Jane, instead of living in Steubenville, Ohio, would have lived in Portage, Oregon, where the pollution would be lower? Of course, I will never be able to know that, right? So how I do calculate the control group? How do I find the control group to be able to figure it out what the survival experience would be for Jane if Jane would have been living in Portage? And so I'm just talking about matching here. So here is again, right? What would Jane's survival experience have been if she was exposed to level of PM that were similar to those in Portage? So remember, so these are the survival curves, years of follow-up for the different cities. So remember, Jane lives in Steubenville, so I observe what the survival experience for Jane has been in Steubenville. I would like to know what the survival experience of Jane would have been if Jane would have lived in Portage, okay? So how I do that? Well, you need to think about what would be all of the confounders, what would be all of the things that could have affected Jane's survival experience. Smoking, drinking, body mass index, and all of that, right? And so what we need to do is to identify a control group. So here is another example, right? So here is Steubenville, Ohio, and because this is an observational study, the makeup of the population in these two cities is different, right? And I'm just making it up. So in Steubenville, Ohio, there is high level of pollution. In Portage, there are low level of pollution. And in Steubenville also, we have more people that have a low socioeconomic status and people that smoke more. So these are apples and orange, right? These two groups, again, if we would have randomized, you would have seen the same type of makeup. But because we are not, these are different. So I observe, so Jane is one of these green. So she has, actually, this is wrong because Jane doesn't have a low education, but whatever. Jane has a low education. How I'm finding the potential outcome for Jane? I'm going to go to Portage and I'm going to take everybody important that is as similar as possible to Jane. And I'm looking at their survival experience, and that will be the potential outcome. I take that difference, and that is the causal effect of pollution. So that's basically, in this context, is that our goal is to estimate the potential outcome for Jane by taking the survival experience for the women that live in a lower polluted area, say Portage, but they are otherwise as similar as possible to Jane. And that is a group of high school teacher in Portage. And so that's just to basically show that that would be an adequate control group. So in this context, an adequate control group can be represented by people that live in a city with an average pollution level of PM2.5 that is 10 units lower than Steubenville, but that is otherwise as similar as possible as Jane. So is regression causal? Well, it can be considered causal if the parametric assumptions are correct. So here we have framed the situation of action A versus action B. The problem with regression is not that it's associational only, nor the results are sensitive to which variables are included. The problem with the regression is they combines the analysis with combine the design with analysis together within a single model. So I wanted to, I just want to give you just a few slides of one study that we recently have conducted, and to give you a little bit more a concrete example above and beyond the toy example I was presented. And so one of the evidence that one of the questions that is still lacking in the literature is, even though there is now strong evidence of adverse effect of pollution, what we don't have strong evidence of is whether pollution is harmful at a level below the national ambient air quality standard. And so what we have done now, we have increased the representativeness of the cohort and linking health experience for people that are in the Medicare system with an individual survey to estimate what the effect of our pollution would have been, also for people that live in areas that are always below the national ambient air quality standard. So these were the most recent standards. The recent standards were reviewed again in 2013, where we have the new national ambient air quality standard for PM2.5, which are now set to 12 microgram per cubic meter. So the question, the scientific question really I'm asking here is there evidence that there is still an harmful effect of our pollution, assuming that everyone will live in areas that are below the national ambient air quality standard? And if there is, it means that we need to lower the standard even more. So to estimate the causal effect, you see now I'm using the word causal effect, and I'm telling you why, of lowering PM2.5 level from above to lower level of the standards. And also for individuals that are always living in areas with pollution level lower than the standard, to see if lowering the level even further will improve their mortality. And also to see the sensitivity of the results to confounding. So when I was telling you about matching and finding someone that is as similar as possible to Jane, right? Well, if I need to match with respect to 100 characteristics of Jane, the number of matches, so the people in this control group will be very small. In other words, your model, your regression model, you will need to include in like a million of covariates, right? When we can do some analysis to figure out which are the important confounders. And then we can adjust only for the one that really matter. And that is important because your analysis will be more robust because you don't need to deal with a large number of variables. So basically what we did, we have linked the Medicare system, claims from Medicare. Everybody older than 65 in the United States is enrolled in Medicare. We know all of their health experiences, but we don't have information about smoking, body mass index, and other characteristics. So we link them with the Medicare Current Beneficiary Survey, which is a phone survey that provides all kinds of information among them. So we have 32,000 people. It's really a cohort study where we have a reference date where people get a phone interview about, all of their smoking, body mass index, health status, and everything. And then we calculate their exposure to pollution 2 years before the phone survey, and then we follow them up over time, prospectively, to look at for hospitalization and death. So that is the map of the level of pollution for the people enrolled in the cohort. So you see there is quite of large variability so this is the number of enrollees, nationally representative, and the average PM 2.5 can be as low as 3 microgram per cubic meter and high as 15 microgram per cubic meter. And so my causal question is, what will be the causal effect of being exposed to level higher than 12 to lower than 12 on mortality and hospitalization? And then if I only take the people here that are already exposed to 12, already exposed to level below 12, would be the effect be also protective? Would the lowering level of pollution even further will increase public health? So we use a tremendous large number of potential confounders, right? So everything about them in terms of individual level covariates, age, gender, and race, area level covariate, all information from the survey. The reason is, remember the question of matching, right? I have some people, so here, let's say I take someone here that is exposed to a higher level of pollution, and I know whether or not this person gets hospitalized for what. I need to know what the health experience for this person would have been if this person would have lived here, right? And how I do that, I need to match, I need to find from the people that live here, all of the people that are close, as similar as possible to this person. These are the confounders, okay? These are the confounders, and these are the variables you include in your regression model. So we analyze many, many of them. And then this is really the thing I want to show you. And I'm just going to take a little bit of time. So this is the full cohort. So this is everybody. And what this blue dot shows are the average standardized difference of the percentage of black in a county, that's the variable, between the areas that are exposed to level higher than 12 and areas that are exposed to lower than 12. So basically what this is saying, that the variable percentage of black in the county is highly unbalanced between areas associated to, they have a high pollution level and low pollution level. So it's an important confounder. Surprise, surprise, right? So places with a higher pollution level tend to have higher representation of people of color. And then you see the blue dots all shows all of the variable, for example, less than high school degree, socioeconomic status, rural score, area that are in rural area, percentage of poor. So we analyze over like 122 variables, right? And I'm just ranking the one that are most unbalanced when I compare an area of high pollution and low pollution. This means that these are the variables that really need to be balanced in order to provide evidence of causality. In other words, these are the variable that shows why we're very far from a randomization. And all of the methods for causal inference, and here I'm showing one, which is called propensity score matching. What the propensity score matching does, you find the propensity score, and then you classify people that are similar to each other based on the same propensity score. And then we have calculated the observed standardized differences after the matching. And so the difference between the blue and the red is one way to show you how with matching, it has not to be propensity score, could be coarse matching, could be exact matching, you improve the balance of the covariate between the area that have a high pollution and the area of low pollution. Indeed, by going from here to here, we are getting closer to a randomization. If you randomize people, this is the plot that you're supposed to see. You shouldn't see any systematic differences from covariate between people that go in one area and the other. The other interesting thing to think about is that if we take all of the people that always live in low pollution level, actually the variable that are in balance are actually kind of different, which is such an interesting thing that we always don't think about, that the level of imbalance of the covariate can actually depend on the exposure level. But that is one way to really going from an observational study and try to approximate a randomized study by doing matching. So I'm just going to show you just the results. So we use a marginal structural model, but we can do propensity score model, or I'm going to show you the regression model. But basically what we found is that these is as a ratio showing the percentage reduction in mortality if we would have reduced exposure to level higher than 12 to lower than 12. So first of all, the blue and red are when I consider all my 120 possible confounders, and the red and the blue is when I only use a subset, just the one that were unbalanced. And so, you can see are pretty similar. We found a strong effect of protective effect both on all-cause hospitalization and circulatory hospitalization. And what is very interesting, and now this is actually happening more and more often on all our studies, actually the effects are even bigger. The benefits of reducing pollution is actually even bigger among people that are already exposed to low level of pollution. So that's something that we've been seeing consistently. And so these are all different type of models. This is the same results by using just a standard regression model, which actually tells exactly the same story. So these are the results. We found the lower long-term exposure to particulate matter from levels higher than 12 to lower than 12. Causally reduced all-cause emission and circulatory emission by 7% and 60% and 6%. In the low pollution cohort, which are the people already exposed to low level, we actually found that the beneficial effects were even higher. And then we found that the results were pretty robust to different covariates that you use as a potential matching. So, well, let me go through the limitation, of course. I mean, I think that we didn't find an effect on mortality because we only follow up the cohort for only 1 year. So we don't have enough power for that. We assume the exposure is binary, but then we also did analysis with a continuous. And then, the good news about administrative data and cohort data, I call it open cohort data, is that with Medicare, there's one thing is true. Every year, there are more people coming in. So you can continue to do this study moving forward. It's called open compared to traditional cohort, because when you have a traditional cohort, which is close to new enrollment, at the end, everybody's going to die, and then you don't have data anymore. But with the Medicare cohort, it's open in terms every year there are new people being enrolled. So I just want to summarize and then talk about a little bit about my team. So I think what I hope to that, one thing I want to communicate with this talk was basically that causal inference and all of this enormous amount of literature, although really important as advance our thinking, it's not a silver bullet. It's not because I use a fancy statistical causal inference method I get a silver bullet, but it actually is a way of thinking more about your study, your question. There is a really nice paper, I think, is a Don Rubin, 2009, and it's called Design Trumps Analysis. It's a very, very nice and beautifully written, and it's really talk about the importance of thinking about the question and the design versus fancy estimation procedure. And so the determining causality is mostly a story of discerning whether the design of the study was successful. Thinking about the question, thinking about the potential outcome, thinking about the control group, thinking about issue about matching. And I think these are like the key principle of doing a rigorous analysis, which therefore you get closer to evidence of causality. So I want to thank you, my colleagues. I mean, these are people that are really central to many of the things I talked today, and they're actually a lot of fun. So Maggie Makar, she's originally from Egypt, And she's a PhD student at MIT in computer sciences. We tried to recruit her in the biostat program, but she decided to go to computer science, which is, I'm very happy because she's teaching me now computer science. She's absolutely a jewel. Corey is an assistant professor in the department and really a very deep thinker in terms of causal inference method. Christine Chorat, which actually is from France. Originally, she's our research data scientist. Georgia, we only call it Georgia because her last name is too long, I can't pronounce. She's from Greece, and another character. And Ander, who just finished the postdoctoral fellow with me and is now a faculty member at Colorado State. And of course, you know, I mean, this is the joy of all I do, and I couldn't do anything without these incredible people. And of course, NIH, an environmental protection agency, as they have been funding a lot of our, and the Health Effect Institute.